Alright, so this video shouldn't be terribly long. I'm just going to kind of go over the answers to the homework. A lot of these are pretty self-explanatory, or in the sense that when you do the math, they're pretty easy. I've circled the answers. I've also provided you with an answer key directly, so you can just look at those answers. But most of these here, 1 through 5, are pretty easy. Speed of light's a given. Wavelength of light, you're just doing the C equals lambda nu wavelength times frequency. You plug the speed of light in for the wavelength. Plug the speed of light in for speed of light, duh. And then the frequency is nu, and you're solving for the wavelength. This is meters, so make sure that the units match up. After that, they're all kind of the same. What's the frequency? Here's the wavelength. Plug it in. Number 4. Photon of light is blank proportional to its frequency and blank proportional to its wavelength. They have to be opposites. So the energy is directly proportional to its frequency. If you have a lot of waves per second, if you have high frequency, then you would have high energy. That's a direct proportion. Lots of waves per second means high energy. That's inversely proportional to the wavelength. If you have lots of waves per second, then the waves are really close together. The wavelength, the length between waves, is tiny. 5 is just a factual thing. X-rays have the shortest wavelength of those 5 listed there. Of those 5 listed there, which one has the longest wavelength? Radio would have the longest of these 5. X-ray has the shortest of these 5. Gamma would actually be shorter than X-ray, but that's not a choice here. Number 6, what is the frequency? Here's a wavelength. You would have to convert these centimeters to meters first before you could do that one. Number 7, the wavelength of a photon has energy. It's the energy. What's the wavelength? So this would be Planck's equation, h nu, and then c is equal to lambda nu. So you can take the energy value, plug it in here. Planck's is a constant. That would give you the frequency. Then you could throw frequency into the speed of light equation to solve for the wavelength. Number 8 is kind of the reverse. The energy of a photon has a wavelength of 9 meters. That is a pretty long wavelength. So you could take that. That's the wavelength. You could plug it in. I'll just switch to blue for this one. You take the wavelength and plug it in. And with the wavelength, you could solve for the frequency. With the frequency times Planck's constant, you could solve for the energy in joules. Number 9 is pretty much the same thing. You have energy based on this frequency. And number 10, a mole of yellow photons has how many kilojoules of energy? This equation, E is equal to h nu, this is for 1 photon. So that's per photon. So when you plug this wavelength in, plug that wavelength in meters, it would be 527 times 10 to the minus 9 meters, you're going to get a speed of, you're going to get, wavelength would go here, wouldn't it? Uh-oh, I need an editor. Alright, so the wavelength would go in for a lambda, and then you would get the frequency, boom. You could plug the frequency into Planck's equation, and you would get the energy for 1 photon. This is a mole of photons. So afterwards, you'd have to say, okay, this is the kilojoules, the energy for 1 photon. You'd have to multiply that answer. You'd say, well, there are 6.022 times 10 to the 23rd photons per mole, and so then you could get the amount of kilojoules associated with a mole of photons. So you have to do a second conversion afterwards. I repeat, energy in Planck's constant is the energy per photon. So you have to convert it over to energy per mole, given this question says we have a mole of photons. So these couple are just fact-based of the following. Visible radiation has the longest wavelength, and gamma radiation has the greatest energy. And we're just saying of these 3 choices, which of the following visible light has the longest wavelength. Red has the longest. The longer the wavelength, the lower the energy. The highest energy of visible light would be violet. So red is the weakest, violet is the highest. Red is the longest wavelength, which means the waves are far apart, therefore there's not as much energy. Violet is the shortest wavelength, so you would get more waves in a second, higher frequency. Number 14 of the following transitions, the blank transition results in the emission of the highest energy photon. So A and E don't work, no and no, because they wouldn't be emitting photons. They're going from energy level 1 to energy level 6 or 1 to 4, so they're actually increasing in energy. They'd be absorbing photons. Same thing with D, that's an increase, so that doesn't work. So it's either B or C. Both of them are starting at 6, but B is dropping the most, so this would have the highest energy level change. The highest energy emitted, a photon of light as it drops from 6 to 1 would be greater in energy than a photon that dropped from 6 to 3. Bohr's equation for energy levels were... Actually, we're not even doing that. So you can scratch 15 off. Technically, that's the answer. You had an equation in your notes you don't need to know how to use. It has some number and Z and energy level and all that stuff. We're no longer using that. But suffice to say, as you go through different energy levels, there's a different amount of energy associated with each energy level. The farther away from the nucleus, the greater the energy of that level. So energy level 1 has the least amount of energy associated with those electrons. Energy level 8 would have the most amount of energy associated with those electrons. And to make it go from one energy level to the next, there's some quantifiable amount of energy. We used to calculate that. We can calculate it, but we are not in this class going to be calculating that. Okay, calculate the energy. Oh, this is just like the last one. We're not going to calculate the energy transitions from one energy level to the next level. So you don't have to worry about 16. Sorry, I didn't delete that one from the homework. 17, a spectrum containing only specific wavelengths. It's called a what spectrum? That's a line spectrum. A line spectrum occurs when, like here, when an atom, this is what we could kind of take from that one section of the notes, when an atom goes from one electron level, energy level, to another energy level, it absorbs or emits, depending if it's releasing or taking in energy, at a specific value. And we will only get values or wavelengths associated with that energy transition. So we end up getting specific colors based on the energy transition. So we get very specific colors. We call those line spectrums. Number 18. Yeah, I actually should have scratched that one. Sorry, guys. 19. We'll talk about the absorption versus emission part. The actual wavelength, not that important. But if it's going from 2 to 6, it should be gaining energy. It should be absorbing energy. I'm not going to have you calculate how much energy as it changes energy levels, and we're not going to calculate what wavelength of light is associated with that. That was removed. I didn't catch it. Number 20, there are blank orbitals in the third shell. Third shell is the same as the third energy level. So the reason the answer is 9 is because you have S's, P's, and D's. You could have a 3s, which is 1 orbital. You could have 3 P's, which is 1, 2, 3 orbitals. And you could have those pesky 3D's, 1, 2, 3, 4, 5. So 5 plus 3 plus 1 is 9. A curious thing happens, though. If you take the energy level squared, and that always equals the number of orbitals. This is a weird fact about the number of orbitals per level. So on the third energy level, there are 9 orbitals. 1 for the S, 3 for the P's, 5 for the D's. So you could answer this question a lot easier if it said, there are blank orbitals on the second energy level. That would be 4. There'd be S's and P's. On the fourth energy level, there'd be 16 S's, P's, D's, and F's. It mathematically just happens to work that the energy level squared is equal to the total number of orbitals. All right, these couple questions here are also just kind of fact-based. There are blank subshells containing which of these only contains one orbital. The D's have 5 orbitals. The F's have 7 orbitals. S's have 1 orbital. D's have 5. There is no such thing as the 1p, so E would never be a choice. You can't have a 1p. You could only have 2p's, 3p's, 4. No, anyway, which of these only has 1 orbital? The 4s has 1 orbital. Number 22, blank orbitals on the second shell. They keep using this term shell. Most people say energy level. So on the second energy level, there's S's and P's. There's 1s and 3 P's. That's 4. Number 23, if the n is equal to 1, the shell contains blank p orbitals. N is equal to 1. The first answer is 0. This is the first energy level. On the first energy level, there are no p orbitals. You might have an s, but there's blank p. There's 0 p orbitals on the first energy level. So you would just have s's. In the second question, all the other energy levels contain 3 p orbitals generally. No, not generally. They do. 24, the lowest energy level for F's is the 4th. 25, the principal quantum number. The principal quantum number is when you see like 3D10, this is the principal quantum number. The energy level is also sometimes called the principal quantum number. Make a quick note of that. The energy level is also called the principal quantum number. So let's read the question. The principal quantum number for the first D sub-level or subshell is the 3rd. The principal quantum number for the first F, when's the first F occur? The first F occurs as the 4th energy level. So for F's it would be 4. For P's the first one is a 3, and then for S's it's the 1s. 26 is kind of that fact about how many orbitals are there per energy level. 27, why hydrogen atom and an electron in blank orbital can absorb a photon but cannot emit a photon. Can absorb a photon. I circled the wrong answer. The answer to 27 is D. Did I type the wrong thing? No, I did. Yes. 27 is actually D. A hydrogen atom, an electron in blank orbital, can absorb a photon but cannot emit it. So the 1s could gain energy, and the photon could excite a 1s electron, but it can't emit a photon from the 1s, because where would the electron go? There's no 0s orbital. The electron can't go down another energy level, so it can't emit a photon in the 1s, but it could absorb it. So I apologize, 27 is actually D. 28's easy. S orbitals are spherical. P orbitals in neon 3, 30. P subshell can accommodate 6 electrons. That would be 3 orbitals with 2 electrons each. 32 orbital does an electron. Greatest shielding. Oh, greatest shielding. So we have the nucleus, and then we have, that's the nucleus. We have 1s, 2s, 2p, 3s, 3p, 3d. And each of these energy levels, S, sp, sp, d, each of these energy levels is shielding the previous layer. Let's kind of zoom in there. So here's the nucleus. We have 1s's, we have 2s's and 2p's, we have 3s's and 3p's. And each energy layer is shielding the nucleus. So these guys are being pulled in, but everything in here is pushing them away. All of these energy levels are pushing them away. We call that the shielding effect, where outer layers are shielded from the nucleus by the inner layers of electrons. So they're shielding it. So let's read this question more carefully now. In which orbital does an electron of phosphorus experience the greatest shielding? 1s would be really close. 2s is still pretty close. Phosphorus's outer shell is the 3p. That's the outer energy level. If you do phosphorus Phosphorus's configuration would be 1s2, 2s2, 2p6, 3s2, 3p3. So the last thing filling up is a 3p3, and it's going to be shielded by all of these others. And 33, the 3p contains 6 electrons for xenon. Not too exciting there. All right, nothing too big here. 34, that's the noble gas configuration for an element. Using a noble gas to represent all the core electrons. And then we have these guys. So if you go 4s2, 4p3, that's going to be arsenic. 37. 37. Boxing 37. Phosphorus. We just did phosphorus. It is a 3p3 at the end. Let's draw its orbital diagram for the end. 1, 2, 3. We have to follow Hund's rule when we get to the end. Hund's rule says you have to spread the amount between degenerate orbitals. Degenerate, that always amuses me. So this means I have to spread the electrons out between the various orbitals before I'm allowed to double them up with opposite spin. So as I look at these, how many unpaired electrons are in this phosphorus atom? In the 3p, there are 3 electrons, and they are perfectly spread out. Whereas if I was doing sulfur, sulfur would be 3p4. And so for sulfur, let's just erase that and try that again. That didn't look very good, did it? Yep, I know you agree. 3p4 for sulfur would have an extra electron in here, and so then it would only have 2. It would have 2 unpaired and 1 paired in the 3p. So 38, there are how many unpaired in fluorine? Fluorine is 2p5. So there's 1, 2, 3, 4, 5, and then there's 1 that's unpaired, which is why fluorine usually takes a -1 charge, because it has space for 1 down or downspin electron. Principal quantum number again is code for what is the energy level of the outermost electrons. So bromine is 4p5 at the end, and that's why we picked 4 here, because it's the 4th energy level, or 4th principal quantum number. All of the following have blank valence electrons of s1. So we're looking at 1s1, that's a 2. Good job. 2s1, 3s1, 4s1, 5s1. These are all found in the periodic table in the same column. We call them alkali metals. Alkali metals. Alkali earth metals are all s2s. Halogens are s2p5s. Noble gases are s2p6. These are not things you memorize. I mean, you know where the noble gases are, but you think about it. You go, okay, where are the noble gases? 2 and 6. Oh, they're all s2p6. You don't need to memorize that. You need to just kind of like grasp it. The chalcogens or chalcogens, however that word is said, I always struggle with that one. That's the carbon group, and so they would be s2p2. Elements with the p6 electron configuration are the noble gases. So the periodic table is often represented one. That is the worst periodic table I've ever drawn. Let's try that again. Also horrible. I can almost hear your laughter from yesterday. Or I guess it would be Friday. So today is Wednesday. So let's, okay, here we go. So we have 2 ways of describing the groups. So this is group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 17, 18. Just counting straight across. Just, counting straight across by group. The other way is to do the representative elements and just do the primary column. So this is 1A, 2A, skip a few, 3A, 4A, 5A, 6A, 7A, and then the noble gases are 8A. And the reason people do this other A system is those numbers end up representing the valence electrons. So noble gases have 8 valence electrons. They are all S2P6. 2 plus 6 equals 8. So they're in group 8A, which is also sometimes called group 18. So the A tells you we're just basically looking at the valence electrons. If it doesn't have the A, we're probably going with the straight up numbering system. The transition metals are often given to a B, but the B numbers don't really follow a pattern that you would expect, and very few people ever use them. So just if you know the A's are the representative ones for the valence electrons, you don't have to worry about the transitions. 42, which group would contain the valence electrons? S2P1, that would have 3 valence electrons. That would be the boron group. Which of the following is correct? This question would never be asked on a test. Just circling it. Which of one of the following is the incorrect subshell notation? So which of these does not exist? Bam! The 2D doesn't exist. Why doesn't it exist, though, is a much more interesting question. On the second energy level, you have space for S's and for P's, but there's physically not enough space at that energy level for another 5 orbitals to fit in around the nucleus. 48, in the P sub X orbital, that X represents the axes on which the orbital is on. So it's on the X axis. So there's also a P sub Y and a P sub Z. And when you get to the D orbitals, they also can have a D sub XY, meaning it's on the XY plane, etc. But we don't worry about those too much. Number 50, a maximum. This one is, 50 is A. F's can hold 14, D's can hold 10, P's can hold 6. And then, which of the following orbitals can only hold 2 electrons? Well, these are orbitals. Every orbital can only hold 2 electrons. Bam. So a lot of people think, well, the S is the only one that can hold 2 electrons. The S sublevel can only hold 2. The P sublevel has 3 orbitals. Why am I making sound effects? The P sublevel has 3 orbitals, so it can hold 6 electrons. But each individual orbital is only holding 2. So orbitals can only ever hold 2. I could have done the same thing with D. The D sublevel has 5 orbitals, so the D sublevel can hold 10 electrons, but there'd be in pairs of 2 per orbital. Okay, so iron is, I think it's B, right? 55 is B, yeah. I just want to point this out. It's quite common for them to group these energy levels together. So these are all the third energy level. This is not the order we would follow it in an off-balls. We'd normally write that 4S before, but after writing it in the standard order, they then reorganized it so all the third energy level guys were together. That is very common, to remove them so that the energy levels are all grouped together, and to put them, 1s, the 2s, the 3s, the 4s, etc. So that is iron, 3d6 right there. Ground state, so I should not have put this question in here. Let's just change this to say 5s2 4d4. And if it had said 5s2 4d4, you would have been great. You would have probably chosen molybdenum. And this is one of those exceptions you don't need to know, is that the electron that's in the 5s is jumped up there. But really you could have just added these together. It's krypton plus 6 more electrons. Krypton plus 6 electrons. Krypton has 36, so I'm looking for element 42, which is molybdenum, or Mo. Okay, so now I want you to take a minute and imagine you have been making a video for your, say, AP chemistry students, and about 2/3 of the way through the video, the microphone cuts off. It cuts off. So you have just this dead air time, and you don't realize it. So for the rest of the video, you're going to see all this writing is already on the screen, and that's because I've already done this, and now I'm doing it again for you guys, especially for you, Lonnie. Yep, this one's for you. Here we go. So we're on number 57. Real carefully read the question. I've already boxed it. This is the Pauli exclusion principle. Pauli exclusion principle says that any two electrons in an orbital must have opposite spin, right? It does, doesn't it? So we need to look at these answers, and when we look at the answers, we have to figure out which one is a violation of the Pauli exclusion principle. Now I'm going to go over all 5 answers and make sure we know exactly what's going on in each of the 5 answers. So in A, I've written Hund's rule down because it's a Hund's rule violation. We look so far, the 1s and the 2s are fine, but that 2p, we have a pair of electrons occupying the same orbital, and we have 3 orbitals that are empty. And the Hund's rule says that the electrons will spread out between the degenerate orbitals, and these 2 electrons in the first of the p orbitals are not spread out, they're in the same orbital. So this guy here should actually be here, boop, like that. And it's not, so that's a problem. So that's a Hund's rule violation. It's not the answer to this question, but it is a Hund's rule violation. B, there's nothing wrong with B. That's the orbital diagram for the element lithium. It's got 3 electrons, so does lithium. I guess theoretically speaking, it could be beryllium plus 1, you know, and if it was beryllium plus 1, that would mean it had lost an electron. But if it's a ground state configuration, then it's lithium. C is the answer to this question. It is a Pauli exclusion principle violation right here. These 2 electrons have the same spin, and they should not. And then D technically is wrong in terms of the way it's drawn. They should not have had this electron here. They should have really put it there. We always go 1, 2, 3, the first, the second, the third box, and then come back and double them up. And then E has 1, 2, 3, 4, 5 electrons in the original drawing. That looks like it might be boron, but it's not standard boron, it's excited boron. So these electrons that should be in the 1s and 2s have been excited to higher energy levels. I wouldn't say they're drastically excited because the transition between a 2s and a 2p is not terribly great, nor is a 1s to a 2p. 58. Somehow the letter M fell off of this, but we're looking for the electron configuration for a ground state nitrogen atom. So before I even look at those answers, I wrote down the configuration for nitrogen. There it is, 1s2, 2s2, 2p3. And then I started evaluating each of these. Good here, good here. What is that doing? It should be over here. So this is not the ground state nitrogen, even though it is 2p3, because that electron should not be doubled up yet. It should be over here. So that is a violation of Hund's rule. B and C have Pauli exclusion principle issues. These have the same spin, these have same spin, so they are Pauli exclusion principle issues. Or PEX, as I wrote here. Sounds like plastic decking to me. And then D is the right answer. I don't know why I wrote nothing down. That should be nitrogen. I'll just scratch through that. There's nothing wrong with it, I guess. We have 1s2, 2s2, 2p3. The electrons are spread out using Hund's rule. Everything's great there. 59 looks... 59 is actually one of those weird exceptions I was talking about in class. You don't have to memorize the exceptions, but you could still deal with them in terms, here's the electron configuration, or the noble gas configuration, and let's just count. We have argon, which is 18 electrons. We have a 4s1 and a 5, can't speak, a 4s1 and a 3d5. 1 plus 5 is 6 electrons, and so that is 24. Chromium has 24 electrons. Normally, we would have written it like this, 4s2, 3d4. But the actual configuration where they shift is this one here. You don't have to know these exceptions to the configurations, but you could easily figure out what element it is just counting the electrons, to be honest with you. Okay, what do we have here? Hund's rule. Hund's rule says that the electrons have to spread out before they can double up. Yeah, have to spread out before they can double up. So let's go through each one, figure out what's wrong, what's right with each one. A, we have 3 electrons, but they're not filled from the least to the greatest. So that is lithium. It's excited lithium. We don't have a Hund's rule issue. We just have an excited electron. B is a Pauli exclusion principle issue right here. These 2 electrons should not have the same spin. C is our Hund's rule violation. This electron should not be here. It should be in the next orbital. There we go. Look at that. I'll just scratch that guy out. So that's why the answer is C. It is a violation of Hund's rule. Normally when we fill orbitals we go 1, 2, 3 and then come back and go 4, 5, 6. If we're doing for p's, that's for p orbitals because p's have 3 orbitals. Sorry, that's for the p sublevel because they have 3 orbitals. For the d sublevel there's 1, 2, 3, 4, 5 orbitals. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and then we've got it all filled up. Answer D is just technically wrong. We usually go the first box, the second box, the third box. First box, second box, third box. And this electron here needs to be shifted over a bit. And then E would be the configuration for nitrogen. And there's nothing wrong with this. This is a perfect orbital diagram for nitrogen. You may see questions like this where you have to kind of like dissect all of the answers and figure out what's right and wrong. We don't ever do the F sublevel other than to skip through it as we go to maybe polonium or astatine or something like that. But we don't actually really ever do orbital diagrams for them because there's too many exceptions in the F sublevel. To diagram something where there's that many exceptions is really a waste of time. There's just too many exceptions to do it. And we're not getting in all those exceptions. And, I mean, if you want to see how many exceptions there are, look at a periodic table that has a noble gas configuration, like the one in the front of the room that's above my desk, and look down there in the F orbital area, in the F sublevel area, and you will see exceptions on, where are we? Gadolinium has exceptions. Neptunium has exceptions. Curium has exceptions. Berkelium has exceptions. Lutetium. I don't think I've ever said LU, number 71. Lutetium? I'm not sure I've ever said that one out loud. And Lawrencium has exceptions. So there's just way too many exceptions down there to make diagramming the orbital electrons even worth attempting. Okay, so this one I'm gonna clear all of this stuff off, start from scratch. We didn't really get to do a very thorough explanation of this when we did the notes, or in one class I don't think we did an explanation at all. So what this is, photoelectronic spectra, or PES, is the amount of energy to remove electrons from an atom. And the way they're doing it is they're taking every single electron off. So for argon is 1s2, 2 I already can't write. 2s2, 2p6, 3s2, 3p6. And it looks like it's kind of written backwards on here. And you're just going to imagine that they are, this energy quantity here correlates to them removing those 6 electrons. And then the next energy quantity is them removing 2 more. And then removing 6 more. And then removing 2 more. So they've removed all of these electrons, and this last energy quantity, which is drastically more than all the others, is them removing the last 2. And so argon has 18 protons, and they've removed, at this point, 16 electrons, and there's only 2 more electrons left. These protons are going to have a crazy, intense pull and attraction to the remaining 2 that are there. So we're going to go through and kind of explain, or I'm going to go through, not we, you're not here, I'm sorry. I'm going to go through and explain why we see such differences in each one. There are 2 key terms we need to use correctly, though. Is shielding effect. Shielding effect is one key term, and the other key term is effective nuclear charge. And so let's kind of explain each of those terms before we get into these. So you have an atom, let's say neon. Neon has 10 protons in its nucleus, and then it has these rings of electrons. Let's call that the 1s, and then we have the 2s, and then we have, right about the same energy level, we have the 2p. So there's 2 things working against each other here. Effective nuclear charge is the pull of the protons on electrons, and shielding effect is the electrons being repelled by other electrons, by not just other, but core electrons. So the 2p is being shielded by the 2s and the 1s because those energy levels are between the 2p and the nucleus, which my nucleus is gigantic in this atom for some reason. So it's being shielded and pushed away by the shielding effect of those inner electrons, where the nucleus is pulling it in. So let's walk through those 2 terms in reference to all of this data we're seeing here. We have 3 elements: argon, neon, and helium, who have all been run through PES. What that means is they've taken one of these elements, they bombarded it with high energy photons, X-rays, gamma rays, and in doing so, these electrons have been stripped off. If they have to put higher energy photons, they might get higher energy electrons to pop off. So they bombard these atoms, electrons get pulled off, and it gets harder and harder to pull electrons off the closer those electrons are to the nucleus, so they have to use higher energy, and they keep getting higher and higher until they can get them off. And so you can see this is the amount of energy associated with pulling these electrons off. Hey, 30, 250, 325-ish, 3,000. So let's just go through each one and explain why would helium be only, 23, 24, something like that? So what does helium have? Helium has 2 protons, 2 electrons. So it only has 2 protons. Its effective nuclear charge is not going to be very high. In fact, it's going to be incredibly low. It only has 2 protons. That's not a lot of pull. To counterbalance that, though, what's the shielding effect on those 2 electrons? There is no shielding effect on those 2 electrons. Those 2 electrons are the only 2 electrons. But since there is no, the effective nuclear charge is so small, those electrons would be relatively easy to remove from the nucleus. So we don't see a high energy peak here. Let's go to neon. 10 protons, 10 electrons. So we see a very similar peak for the first 6 electrons for neon. But the 1s orbital for neon, much higher peak. We need to figure out why it's such a high peak. So as we look at this, the outer electrons farthest from the nucleus, 2p6, they're going to have A, the most shielding, because they have 1s's and 2s's in between them in the nucleus. But B, there's more effective nuclear charge. There's more protons pulling on them. So those two things, again, working against each other. And within neon, you need to be able to explain, why is 2p6 less than 2s2? That's a shielding answer. The 2p6 is shielded by the s's on the second energy level and the s's on the first energy level. Why is the 1s here so much more energy than the 1s here? That's an effective nuclear charge issue. At this point, when you get to this 1s, you have removed these electrons and these electrons, and the 1s electrons are the only 2 electrons left on the neon's 10 protons. And therefore, those 10 protons are going to have an extremely intense pull on these last 2. Because the effective nuclear charge, 10 protons, is greater in neon than the effective nuclear charge of helium, 2 protons, it's going to be much harder to remove those 2 electrons, so they're bombarding neon with much more intense energy to get those 2 electrons off. So, same answer kind of for argon. We have 18 protons and 18 electrons. Why is the 3p6 so easy to remove? Think about it for 3 seconds. Why is the 3p6 so easy to remove? Is the answer effective nuclear charge, or is it shielding effect? It would be, wait for it, shielding effect. Yeah, it's got to be a shielding effect. These 6 electrons are shielded from the nucleus, from these 18 protons. They are shielded by 3s, 2p, 2s, and 1s electrons. They're shielded by all of those electrons. And if they're being pushed away from the nucleus by all those electrons, it would take a lot less energy to completely remove them. Which we see that right here. Look, this is around 15, which is less than either of these other ones. So these electrons were easier to remove because they're being pushed away by all of those electrons. So we take the first, then we've taken some more. Again, that's on the same energy level. So that 3s has just about the same shielding. A little bit less because it's closer to the nucleus, but not quite as bad. Alright, so I just got distracted. Like 3 people just came in here, so I've completely lost my train of thought. So let's just talk about argon as if I hadn't been talking about it at all. So I think I had just said these 3s and 3p were being extremely shielded from the nucleus, which is why there's not a lot of energy needed to remove the 3p or the 3s. Then we've already removed these, and we get to the 2s and the 2p. So these are less shielded. There's only one energy level shielding them from the nucleus. We now have 18 protons and 10 remaining electrons. So these 10 electrons are having a much greater pull to the nucleus than they were previously, which is why we see such large values associated with removing these electrons. And then we've got these gone. And so we're down to just 2 more. So at this point, we have 18 protons, and only 2 of these electrons are left. All the other 16 have been removed. So those remaining electrons are going to be pulled in. So we have 18 protons, and those remaining 2 electrons are really going to be pulled in tight into a really tight orbital to the nucleus because the effect of the nuclear charge is really starting to dominate this. There is no shielding. So these guys, look at that, 3,000. That's a factor of 10 greater than the previous 2 electrons removed. Let's also look at this. As we go from helium, these are all 1s. Why do we have 20, 870, 3,200? That is the effect of nuclear charge. That increase on the 1s is all based on the effect of those protons pulling the electrons in. 18 protons have drastically more pull than just 2 protons. All right, let's see if we can answer these 2 questions now. Explain why the energy needed to remove a 1s electron is greatest in argon. Effective nuclear charge. Sometimes written as Z effective. If you look in the textbook, I think they write Z effective in there as the symbol. Z effective stands for effective nuclear charge. Z is often the symbol for the number of protons in an atom. Why does it take less energy to remove the 3p than the 2p in argon? Shielding. Electron shielding. The electrons are shielding the nucleus, and therefore they're easier to remove. Do you get that, Moody? You good? You good?
I got it. Definitely got it, Mr. Murphy.
Thank you. Thank you. Have a good day. And that ends the video. Little special guest appearance by Moody there. Have a good day, and goodbye.